Conversations in Artificial Intelligence. Paolo, your host, and welcome back. So today we're going to go into a sector that is a little bit unusual, but going to impact our lives and the lives of people around us, especially the ones that we love very much. So what happens when somebody calls first responders? You have some medical problem, you need an ambulance, you call the police, you call any other service that has to come right away. What if these people find an obstacle in their path to come and rescue you? What if they do not have a clear vision of what it is, the quickest way to get to you, take you and bring you to the hospital, or save you from a bad situation? So that's what happens today. You might not believe it, but things like Google Map and other technologies that are available today do not solve this problem. Today, first responders cannot get to you quick enough, or cannot get to you to the quickest way possible. So with me today, we have Kurt Brandt, who is an innovator, who has been a scientist and entrepreneur for a number of years, and he has recently found a very interesting artificial intelligence startup company, LinkThings, and we will see why the name cannot be the most accurate than this one. So Kurt, how are you today?
I'm great. Thank you. How are you doing today?
I am doing very well. It's a fantastic day here in California, very early in the morning. And tell us a little bit where you're calling from.
So I'm calling from Mequon, Wisconsin, and it is not as beautiful as it is there in sunny California this morning.
How did you get into AI? Why we're having this conversation today? Why we're talking about AI? How did the AI get into your life?
AI has been involved in my life ever since I graduated from college, and I started a first summer internship, and I used gradient descent to match curves for infrared spectrum. And at that time, there were the tools that we had today, so that was hand-coded in Fortran. That actually led to a whole career of applications where I've used AI, from industrial applications where we're able to predict the return and warranty information for 16 manufacturing plants throughout the world, saving our customer $12 million in the first year, to our first patent, which we filed in 2005, which was titled Trainable Sensor Network, in which case we used multiple different types of sensors and a specific type of indicator called higher order statistics, along with a neural network, to be able to identify chemical species without having to know the spectrum of them in advance.
So you've been involved in a lot of R&D. So just for our public, what you did is you created an R&D company that basically rents out the ability to do research and development, and created solutions based on algorithms for companies around the world. And at a certain point, you went into this thing that is called predictive mobility. What it is predictive mobility?
Okay, so predictive mobility really addresses a problem that's emerging, and that emerging problem is that people and vehicles are moving faster and need greater degree of information to be able to improve this faster and more accurate motion. But most specifically, what we're doing is we have more accurate information and forward-looking information. And this solves a key problem that was introduced to us of first responders being blocked at rail crossings.
So why they get blocked at intersections, and why they cannot get there in time today?
Yeah, so it turns out that in the United States, freight trains block intersections something like 20% of the day for an average of 8 minutes. And I was very surprised when our customer called us and said, this is our problem, and we've been looking for solutions for 5 years with 5 other communities. We've looked at mapping programs, we've looked at all sorts of software, and we have no solution that helps us get across those intersections. And so the problem is that for critical types of injuries like heart attack, stroke, and traumatic injury, you have something like 4 minutes to get to the patient. And if there's a freight train halfway between you and your patient, say 2 minutes away, and you get blocked for 8 minutes, well, then that patient is not going to survive. So this is a critical problem for emergency response in many cities all across the United States.
Once you discovered this critical problem, you developed a new company, Link Things. What it is that this company does?
So our predictive mobility solution, what we do is we place our cognitive sensor devices out in the field, and they collect information real time, which then gets processed in our cloud applications to predict future locations of vehicles. And we push that information out to our customers in real time through different types of applications, APIs, if they have existing systems like a computer-aided dispatch system or mapping program. Or we also have user interfaces which are designed specifically for our customers, and they provide information to customers that have specific information requirements.
Can you help us understand a little bit better what is the general use cases around this solution?
Sure. So our solution provides a number of value propositions in the smart cities arena. We start off with traffic. So there's 152 million users of mapping programs of actually just Google Maps alone in the United States. And they've recently offered a new commuting application, which helps them commuters get to their job on time. However, the problem is that the average commute time in the United States is 24 minutes, and the average freight train blocking time is 8 minutes. So if a freight train is in your path between your home and your commute destination, then 1 out of 5 times your commute is going to be 30% longer than predicted by Google and the other mapping companies. So there is an interesting study that shows that for every minute longer of commute time, it feels the same as your boss telling you he's reducing your salary by $1,000 per year. So commute time is one place that helps general citizens across the whole United States. In the logistics area, it also has a very high impact. So carriers cross and get blocked by at rail crossings about 1.4 billion times a year. And a study at Georgia Tech indicates that each time, actually, that the average cost per hour for a carrier delay is something like $194. What that translates into the average train blocking a carrier is $25 each time that happens, times 1.4 billion times that they're blocked. Turns out to be a $35 billion problem that nobody's really addressed. That's the time and money savings for logistics, but that also fits into the sustainability area as well when you start thinking about the fuel usage and the carbon footprint that's added just waiting for at crossings.
So if we look at it from a purely business perspective, so you are innovating in the space of predicting what path to go and avoid delays. But who are really the economic customers, if you like?
Yeah, so in fact, just the emergency response part of this market is fairly significant based on the price that we're charging right now for the usage. Just the emergency responder market is something like about $3 billion addressable market. For the first response application, it's the government, and that alone is a $3 billion opportunity. So that's one of the things that we've focused on because of the high value. It's an urgent solution with a high value in saving lives. And then at the same time, as we're building that out, we have the ability to start serving logistics customers. And those customers are Amazon, FedEx, UPS, United States Postal Service, and a whole plethora of transport and carrier companies that have systems in place now which help them do the routing, but do not have this piece of information
we have been using Google Map for a number of years. So now you're coming up saying that, no, that doesn't work really well. Why Google cannot predict to the extent that you can do?
There's a couple different other solutions. So Google, then there's schedules and there's satellite data, but none of them have the detailed information required. Now, if we think about just Google, for example, they get their information by collecting it from people who have their mobile devices on their person. And so in order to understand the traffic flow at an intersection using their methodology, you have to have a significant number of people that are moving through that intersection to be able to tell whether the flow is increased or decreased or changed. And so unless you have that flow of persons with their connected devices, you don't have the information. And that turns out to be most of the roads in the United States. Google works great in congested areas, and it solves the problem of understanding congestion when there's other vehicles, because that's what it does best. But it doesn't work where it's 2 a.m. in the small town and the train is blocking the intersection that the ambulance needs to get to address their patient. So most of the cases in intersection in the United States are not helped with that type of piece of information. And so what we do is we have the information based on our sensor data, which gives us high accuracy, but then a step further, for the first responders, what's important for them isn't the history of like, hey, what is the history of the congestion at intersections? What they need to know is if they're leaving the firehouse now and they need to go to a patient that's 4 minutes away, and suppose there's a train 2 minutes away, they need to know now whether or not they're going to be blocked in 2 minutes with that train so they can take a different route. And so that's what we provide them, is that accurate information, and that forward-looking information allows them to make decisions in advance of running into problems.
This is a level of precision and a coverage of use cases around mobility that is much higher than what we experience when we use Google. And of course, this is of interest for those for whom the mobility going from one point to another is critical. Going into the shortest amount of time is a critical situation. So as we said before, these people are the first responders, the ambulances and police, but also the businesses that make money out of delivering stuff at scale. So for them, delays over the network at the end of the year sum up into an operational cost. And so they want to reduce this. But the biggest question that we have is, why didn't people do it 10 years ago?
Well, I think we could come up with the idea 10 years ago, but I don't think it could be implemented 10 years ago. And what's changed, there's a number of things that have changed significantly in the last 10 years. Number one, if we start at the beginning of the signal chain, it's sensors. So with all the autonomous vehicles and smart vehicles on the road that may not be autonomous yet, but still have the sensor information, there's a huge amount of sensors that have been produced in high volume. And so that allows us to leverage those sensor technologies to produce a much lower cost, even though complex, a lower cost system. So that's one place that has changed in terms of the economics of being able to deploy a solution like this. The next is the network capabilities. So the cost of transmitting machine data through cellular and other networks has come down dramatically, and there is more solutions to that type of infrastructure that weren't around 10 years ago. And then of course the availability of cloud computing and the ease of building distributed AI solutions is completely different now than it was 10 years ago. And 10 years ago we were still coding our own AI algorithms from scratch, and now there's so many toolkits that leverage GPU and other types of devices which are so much easier to use than they were a decade ago. So technology has changed a lot, and then the economics of the technology has changed a lot as well.
So fundamentally, we have three things here, if I understand it correctly: ecosystem of technology, lower down the costs of computations and handling the data, and the simplification of the process of creating and deploying machine learning algorithms.
Yeah, I think that's true because the basic technology structure that we have now, we've been using this type of structure for a long time, but the use cases have been different before. They had to have the cost of implementing was much higher 10 years ago than it is today. And so that lower cost allows us to access new markets that were really not accessible to us in the past.
Let's dive into the science, into the secrets here. So what is the technology doing and how many pieces do we have?
There's a couple of key pieces to this, all of which we've used in other applications over the years. But the first is one of the ways we use AI in this case is to improve signal to noise in sensors. So historically, a lot of people use analog and digital filtering. We use actually a mechanism which is predicting the result of the sensor instead of filtering it. And it turns out that we get a factor of 10 improvement in signal to noise that way. So we can use low-cost sensors and get great results.
So the sensors are an important part of what you're doing. You're not just a software company, you also have the hardware. The hardware is cheap.
Yes. We design all the hardware ourselves, and we have it all manufactured here in Wisconsin about
that's great.
5 miles from our facility. So we have really good control over all the hardware manufacturing. So the second piece is that we use multiple different kinds of sensors in all our applications. And that's really a biomimetic, copying biology in humans, because the way humans differentiate different objects and things in their environment is they don't use a single piece of information. They use multiple pieces of information. Our eyes has multiple ways that it collects information, and it uses your eyes, your nose, your ears, all different parts of your senses to understand your environment. And we do the same type of thing. We use multiple different types of sensors with a neural net that combines that information to help categorize the environment around the sensors. And what that does for us is provides a better confusion matrix. So what that really means is that if it's raining or snowing, or if there's coyotes running down the railroad tracks or whatever, all these different types of things that can interfere with your sensor information. If you have one sensor that can be very sensitive to those types of changes, when you have multiple sensors and you train them as a collective, then as a collective, it's a much more powerful piece of information because it's resilient to all these different types of ways that can be fouled and interfered. So that's really the second piece of our solution. And that's a distributed application. It occurs both in the edge and in the cloud. And then the third area is somewhat more obvious, and that is the predictive piece. So we're collecting all this information, and from that, basically, we are determining what the speed, the location, and the length of the trains are, and use that information in a model that helps us then predict where that train is going to be in 1 second, 10 seconds, 20 seconds, and up to in a number of minutes in the future. So we're doing future predictions about the locations and speed and direction of objects, in this case, trains.
So basically, this is a pie with 3 layers. The first layers is the layers of having sensors, if you like, watches at the ground. And these sensors normally would require lots of electronics to work with, but you are simplifying this by using artificial intelligence inside the sensor itself with AI, so that the sensor doesn't cost a lot of money. Then the second layer of the pie is making these sensors working synergistically, so that they all together offer a comprehensive vision on what is happening. And then the third piece of the pie is basically predicting, now that we have all the overview of what's happening in all the various positions in the city, predicting where the ambulance has to go. So that is another algorithm. So I'm curious to know if deep learning plays a role here. So deep learning, for whoever is tuning up and has not heard of artificial intelligence before, is the latest evolution in the algorithms arsenal of artificial intelligence. So I would like to know if that plays a role here or it doesn't.
Yes, so we have different types of AI in different parts of the signal chain, and some deep learning is used in this application, but in general, we're using actually some other types of algorithms, which also gives us some of the benefits that you would get with deep learning, but it doesn't have the computational requirements. So we can do it more efficiently with a smaller amount of processors. And that's important for us because we're doing a lot of this in a distributed environment. So both at the edge and in the cloud, and we're doing it in real time. So a lot of deep learning applications are fairly time intensive, and we need to be able to update our models in real time because the environment's continually changing. So we do some types of deep learning, but in fact, we're using other types of algorithms that are emerging that solve some of those problems of computational processing power requirements.
So one of the problems that we have in artificial intelligence that concur to the cost actually of providing the service is basically having these algorithms working, but also teaching these algorithms. And very often in today's technology, we hear people utilizing the most advanced algorithms in AI, but these are also the most expensive to maintain sometimes. How do you mitigate, if in any way, that cost in your solution?
In our solution, we use something called hyperparameters, which are used to really configure our algorithms. And for a domain application such as trains and ambulances, those hyperparameters are part of a solution that we have for self-optimization. And as long as we're not trying to change dramatically what we're trying to detect, our system is continually teaching itself. So and one of the other challenges, because we're implementing these sensor systems at a whole bunch of different environments, right? So they're all at crossings, but each crossing is, different weather conditions, different patterns in the environment there. So all these systems, in order for us to be able to even implement them in an effective way, they have to have an amount of resiliency in order to, built into this design. So that's something that we've actually worked really hard on to develop a mechanism so that somebody can just take one of our devices and put it up on a pole and point it in the right direction, and no matter whether you have piles of snow like here in Wisconsin or tumbleweeds in Oklahoma, all those types of interferences get trained into the application on its own. However, if we try to apply our solution to a completely different application, then there would be some additional training and learning involved. So for example, if we wanted to, instead of solve the problem of trains at crossings, wanted to look at solving the problem of boats in harbors, we'd have to make some modifications.
Can your solution be customized by different customers?
I'm going to look backwards on that question, because the solution we have now actually is one that has a great business application. But before this application, with the same circuit boards, the same software, we did 25 other applications in a variety of situations which seem completely unrelated. For example, the first solution that we performed when LinkThings was formed had to do with solving one of the top 5 problems in maintaining the F-35 fighter. So we use the same technology for that application, which is completely different than the application that we're working on now in predictive mobility. And we've also used it for smart kitchen applications. We've used it for agricultural applications. We've used it for manufacturing applications. And even currently today, it's being deployed with another company that wants to use this technology and put it in campuses and schools to watch the traffic of people in the school and identify things like people with metal objects or potential first shooters. So it has other applications even today in the exact format, different box, but same hardware, circuit boards, and software.
So we want to help the first responders, and we are going to fill up the cities with a network sensors that can tell what is happening everywhere. What do you think are the societal implications of this, and how do we avoid to become a society where the government, or even worse, monopolists can dominate, control people's freedom?
The technology provides tools for people to use, and our technology does not identify individuals, it identifies objects. And so in our current applications, and even applications that we're deploying at schools, we're not looking at individuals to limit their abilities, but really to help in securing their safety and effectiveness in the world. Obviously, there's certain countries in the world that have a different viewpoint of the control that they want to implement over their citizens. And so I think from the standpoint of being a technologist, I have no control over that. So that is actually another issue in terms of how the people that have access to this information can use that.
So, but in terms of, and I want to look into this just for a second. I don't know if any regulation exists today, but when you will provide the service to third party, let's say that you provide the service to the police, the service will be provided in a way that it tells only how to go from A to B in the shortest period of time, or will be provided in a way that it gives a map of all is happening in the city with all the details of where is the traffic, how the solution is provided, and if that has ever been part of any thinking.
Absolutely. So when we first were talking about this with first responders, there was this question. They said, well, we really don't want to give citizens the map of where the trains are because we're afraid that they're going to race the trains, and we're afraid they're going to do this and that and the other thing. You brought up two different types of user interfaces, one which is a map of telling you everything that's going on in the city, and that type of information we provide to the communities, and we don't provide that view of the information to other people. So for the APIs that work with routing and dispatch systems, they only have the information about the change in delay time. And for applications designed to work with, for example, Google Maps users, all that is it's the input is altering the routing information that they would normally have. So the standard user doesn't have a view of the whole data set. They only get the use case that they're supplied. In this case, it's routing them more quickly from point A to point B.
What is a use case that is not possible today, or what it is a limitation of a technology today that you're hoping is going to improve in the next few years?
Some of the use cases that aren't possible today, but that are emerging and I see being in use over the next 5 years is, for example, applying this to transit. The problem with buses and commuter trains is while they work on schedules, they're typically not correct. And that provides frustration to the users. As we start using predictive mobility on buses and trains to provide real-time updates on schedules, those types of things can change. So in Wisconsin, if you're waiting for a bus and it's snowing and sleeting out, you want to know when that bus is going to be there. So that type of information is starting to be utilized by various types of transit companies. And I see over the next 5 years that's something that hasn't been available in the past, and certainly I expect to be highly available and ubiquitous over the next 5 years.
Is there any technological innovation that is necessary to support this type of applications?
Well, I think to provide the real predictive mobility application, it's a matter of building the predictive tools that can effectively take all this information and provide the future prediction. And that's the type of thing we're doing now with the trains. So our technology, the way we're developing, can be applied to these other applications, as well as other players in the industry who adopt the use of predictive mobility.
Is there a limitation that you envision is going to be removed?
Yeah, I think what's going to facilitate a wider scale adoption of predictive mobility is a combination of things. Number one, the ability to collect more information from more places. So as the infrastructure evolves, and we start to get 5G as an example, is a way to increase the density of communication that you can receive at low cost. So as we continue to improve our communication infrastructure, giving more access points at lower costs, that will be a key differentiator in being able to implement these types of solutions where we have accurate information from a lot of different places. So that is certainly one area. And then on the technology side, on the AI side, the developing more effective algorithms, which, and we alluded to this before, we look at deep learning, which can provide some great insight, and it can be adaptable, but it uses a tremendous amount of resources in order to do that. And as we develop improved algorithms which can use fewer resources and get answers in a shorter amount of time, not only in the cloud, but in the edge computing environment, then we'll start to see a lot of exponential improvement and adaptation of predictive mobility type of applications.
I want to summarize what we have seen here today for our audience. So artificial intelligence once more proves that it's having an impact in an enormous amount of domains in our life. And what we discussed today is basically how to get ambulances in the right point to the right patients that need help at the very right moment. And that's not possible today. Today, there is a delay from when the ambulance is dispatched from the hospital to when it arrives and takes care, and the person takes care of the person that is in need. Kurt is working for enabling police to arrive on time once they get to receive the call, with a combination of artificial intelligence and devices. So this is, if you like the big words, this is a combination of artificial intelligence and Internet of Things. But what is working today is only the beginning of something that is much bigger, because tomorrow this technology can also be used by logistic companies. They can optimize their network of trucks and delivery solutions so that they save on costs, because they can estimate where to go with where and when to go from a place to another with a much higher precision. But that's not yet all of it. There is more to come for the people like you and me. And so what it is that, for example, today you had to wait for the bus, you have to wait for the metro, you have to wait for the train, but you don't really know when it arrives, especially where conditions are variable, so either weather conditions or other type of conditions. And with this solution tomorrow, you will be able to have a mobile app that tells you the trains will arrive in that station at that exact time, so that you can utilize your time much better, and rather than wasting 15 minutes or 20 minutes on the pavement waiting for the train. So that's what we learned today. That's the future that is coming. And if you have additional question for Kurt, please reach out, comment below, or reach out to me. If you have other suggestions, please let us know through emails or comments. And for the time being, please look at the material below in the section below the video, because there is a lot of additional information that we're going to provide. And thank you so much for being here. And Kurt, it was a great pleasure having you here, and such an interesting technology, but also a business solutions that has a potential to impact really, I'd say, the lives of people in a very meaningful way with artificial intelligence and the Internet of Things. Thank you, Kurt.
Thank you very much.